and you plug them into a matrix as the columns. If the determinant of that matrix is positive, they're positively oriented. If the determinant's negative, they're negatively oriented. And an isometry will preserve the orientation of an n-frame, provided it has positive determinant. Like this has a generalization, not with cross products, but something else in n dimensions. I said I wouldn't say any more about n dimensions. I seem to be talking about n dimensions. So, now what do we care about in here? Well, differential geometry, right? So, here's the theorem. Let alpha be nonlinear regular curve with, for an A-frame, TNB, all right, curvature kappa, and torsion tau, right? Define, let F be an isometry of R3, and alpha bar equals to F composed with alpha. All right, a curve with, for an A-frame, T bar, N bar, B bar, a curvature kappa bar, and torsion tau bar. All right. Then, all right, then what? T bar is nothing more than the push forward under F of T. N bar is the push forward under F of N. B bar is the push forward under F of B. Kappa bar is equal to kappa. And tau bar is equal to tau. Well, that's not quite true. Tau bar is equal to the determinant of the push forward times tau. So if the isometry is an oriented one, if it's one which is formed with a rotation, not a, a determinant one piece for the orthogonal part, then the torsions match. All my chalk nubs are getting small. I should have brought myself a longer nub. Oh well. So here's the proof. So let's see here. Oh, I said arc length. Did I say? I meant arc length. Arc length parameterized. That's mostly just me being lazy because I don't want to fuss with the speed factors in the proof. All right? That's just a point of laziness on my part to assume arc length parameterization here. But proof. So What's T of S? T of S, what was it? It's alpha prime of S, right? That's our definition of unit tangent here. And T bar of S is alpha bar prime of S. But what's that? I guess I would define it right here, right? So that would be F composed with alpha prime of S, right? But what is that? Well, that's the push forward, right? That's the push forward under F of alpha prime of S. In other words, that's the push forward of T. Find T of S there. So that's part of it. Up till now, we didn't even need to use the big guns, right? Like, this is still true even if it's not an isometry. We haven't not yet used that it's an isometry here. But next, Frenet normal, what? So the Frenet normal, n of S, is 1 over kappa, right? 1 over kappa alpha prime prime. Where what? Kappa is what? The length of alpha prime prime, right? All right, so the theorem in the notes that I told you guys to look at, and I kind of skipped over, but it's, well, I don't know, I probably should have just worked out the cases of the theorem we need to use. Honestly, like, let me just take 2 minutes to do it. So if it's an isometry, what's the formula for F? F of alpha of S is just equal to what? It's equal to R of alpha of S, right? Plus whatever the translational piece is. Let's call it A. I mean, you can write it like that, okay? It's an orthogonal transformation, and it's a translation. What happens when you differentiate this? So this is alpha bar of S, right? What's alpha bar prime of S? Well, that's 0, and you get R alpha prime of S. See, this is where reading Kuhnel probably hurt my notes. If I had not been looking at that book, I would have given you a much lower tech proof of this, and it's really not complicated. Once you have that formula, if you differentiate it, and then differentiate it again, what's next? This is constant, so it just... When you have a constant matrix times a vector of functions, when you differentiate it with respect to the parameter of the function, the matrix just sits there and does nothing, and you differentiate the vector. It's how it works. It's just that. And you can keep doing this. Third derivative, right? Yep. But anyway, what this means is that the push forward of alpha prime is, well, what? Excuse me, this shows us that alpha bar prime of S is the push forward of alpha prime of S, right? This tells me that alpha bar prime prime of S is the push forward of alpha prime prime of S, right? Now, how is the normal related to alpha prime prime? We know what, like the normal is, what is it? Well, alpha prime prime is of S is equal to the curvature as a function of S times the normal as a function of S. So many of S's, good grief. In this context, there's no other piece because we assumed unit speed, right? So the tangential component to the acceleration is 0 because like v is constant. So the dv/dt term here, which would be like you discovered in problem 33 of your homework, where you got that curvature, it's got related to dv/dt squared, and the other term, like if you look at problem 33, this is related to that. But anyway, so that, right? So, so what do we got here? F push forward of alpha prime prime is F push forward of what? Kappa n, right? But it's also equal to alpha bar prime prime of S, right? So I've got the push forward of the normal is equal to alpha bar prime prime of S over kappa. And I have some argument here, I think, then, that I need to argue that the, oh, yes, da. So kappa bar is what? It's the length of alpha prime prime of S, alpha bar prime prime of S, right? But that's also equal to what? That's equal to the length of the push forward under F of what? Alpha prime prime of S, right? But it's an isometry. So that means the push forward of, which is what? I mean, that's the same as the length of alpha prime prime of S, which is by definition kappa. So that proves that kappa bar is equal to kappa of S. So we get the curvatures are equal. And once you know that's equal, then you can come back up here and replace your kappa with a kappa bar. And then, lo and behold, you've got n bar. So the push forward of n is n bar. And then how do you get the binormal? Right. We just use this identity and what we already have.
So the get push forward times the push forward of t bar cross n bar.
Right. But when we put t cross n over here, that's b, right?
Yeah. So we don't have to put the bars. Well, no, we put b bars for that.
Well, I mean, we have.
Well, b bar.
So t bar cross n bar should be equal to determinant of f star.
Well, b bar still isn't involved in the push forward t either way, so you wouldn't need to calculate b bar.
T cross n like that, right?
Yes.
So, so this is, by definition, this is equal to b bar, right? But by definition, this is also equal to b, right? So if the determinant of f star is 1,
Then b bar is equal to
then push, yeah, if determinant is 1,
but we're assuming it's 1 because it's an orthonormal basis.
is that right?
Yes.
I think the theorem doesn't say one way or the other. I think it's like open to the possibility that the determinant of that is plus or minus 1. That's why, I mean, the formula, if you look at theorem 3.3.4, it's got b bar is equal to the determinant of f star times f star b, and that's consistent with what we have here. Curvatures match, as we've already seen, and the torsion either matches or it's off by a sign. All right, I'll let you look at the proof of that. It's very similar to what we've already done. So, the end is near, folks. I'm almost done. So definition, alpha and beta from I to R3 are congruent if there exists isometry such that beta is F composed with alpha. In other words, two curves are defined to be congruent if you can move one to the other by an isometry. All right? And I have a formula in the notes. I'm not going to write it down here because I want to get home. But I have a formula in the notes where what I did was I plugged in the formula for the helix into that awful isometry we've got moving one frame to the other, and I give you the formulas for that. So in other words, I formed beta by taking a known isometry, which is rather ugly, we derived it today, plugging in the equations for the helix. That gives me a congruent curve to that helix. And the formulas are given on page 71. They're quite onerous. I mean, it does make a pretty curve. It's this, but it doesn't make for pretty formulas. Anyway, definition. It would be nice if we actually put these into some like plotting software, right, and saw it for our own eyes. Unfortunately, if we had Maple here, I'd do it. But like in GeoGebra, it's just Okay. Well, anyway, all right. I'll let that sit right there. R3. I mean, I'm no fanboy of any of these, honestly. Maple's easier to use. Anyway, okay, so these are parallel. What does it mean for them to be parallel? If there exists P in R3 such that beta of T is alpha of T plus P for all T. I'm assuming that the domain of these curves is the same to avoid this conversation getting much longer. Of course, you could do things like take subsets of curves and compare them and, pare the domains down so that you can compare them appropriately and play all those kinds of games, but whatever.
Wait, so in R3, parallel lines don't really have to follow the same rules as R2?
What do you mean?
Like the helix thing, like if you had two helixes that were like perpendicular to each other, that doesn't mean they necessarily touch.
You could have two parallel lines intersect in this definition.
Yeah.
Like,
But they wouldn't touch.
they could.
Oh, they could.
Like, if I just, I could just, like those would be parallel circles according to this definition. They don't, if we can think about these in time, they don't intersect. You know what I mean? Because like this point, if we start here, then we start there. Then we go up here, then that point's up here. Then we go down here, and this point, we go over here, and then that point's up there, and so forth, So they're not, they intersect as point sets, but they don't collide as paths. All right, proposition. Alpha, beta are parallel if and only if alpha prime of t is beta prime of t for all t. And furthermore, if alpha is parallel to beta and there exists T naught such that alpha of T naught equals to beta of T naught, then what? If you have two parallel curves and they match at one point, then they're the same stupid curve, right? So that kind of is what you were searching for. But again, this is a generalization of the concept of parallel over our usual one. And then finally, theorem. Arc length parametrized curves, and this is really the punchline right here. Arc length parametrized curves alpha and alpha bar from I to R3 are congruent if and only if kappa bar is equal to kappa and tau bar is equal to plus or minus tau. So I oftentimes tell students in Calculus 3 that, there are actually two more results, I'll talk about them in a second here, but this is essentially why curvature and torsion are interesting. They're in some sense like the DNA of a curve. If you give me the curvature function and the torsion function of a curve, you've told me what curve that is. See, because if you give me two different curves and we calculate the curvature and torsion for both of them and they match up, that means that they're the same up to a rigid motion. And that's congruence, right? And the proof of this is just nothing more than the mathematics we've been looking at today. And I personally find this to be a very, very neat result. And and then you can use it to prove other stuff, right? Like he's got a list of some things. And Neil has further results, but the one I have proved in the notes: if alpha is an arc length parametrized curve, then alpha has constant curvature and torsion, if and only if alpha is a helix. Right? So we know that the helix has constant curvature and torsion because we worked it out the other day. That was one of my examples in here, right? And so then the claim then is that if you had another curve that had constant curvature and torsion, you could prove that it's a helix because you can, well, why? Because if f is an isometry, then an isometry composed of the helix is also a helix. But theorem 3.34. Well, anyway, I may be missing something here. Well, anyway, I think I've taken enough of your time. I hope you enjoyed this chapter. Past this, we're going on to study surfaces. All right, so we start studying calculus on surfaces. So next up, in Calculus 3 for a while we talk about curves, and then later we talk about like surfaces to set up surface integrals. So now we're going over to that world of ideas, and there we're going to find out that it's not like curvature and torsion. There's something more complicated that we need to do to understand the geometry of surfaces. It's much more linear algebraic in nature, but not as complicated as, say, real analysis or anything, but just linear algebra. Anyway, thanks, guys. I wonder if my battery's out. That would be sad. La la la. Oh, phew.